Hello students, we are at topic 14 on acid-base equilibrium. This is a continuation from the chemical equilibrium and solubility products which you have learned in JC1. And if you recall some of the things I mentioned before, when we are dealing with acid-base equilibrium, we are still very much focused on a system at equilibrium. So that means that the construction of the ice table for easy doing and then as a way of solving problems is highly useful. Yeah, so for this topic, I would advise you to continue using the ice table to help you solve. Although along the way, you might realize that using the ice table might not be absolutely necessary because eventually the outcome seems to be the same. Yeah, but it does help you to focus your mind and then think about the variables and think about the assumptions which you have made when you are working through the problems. Okay, so without further ado, I will just jump straight into the introduction. Yep, so you probably need to recall what you have learned in topic 4 under reactions and stoichiometry on the Bronsted-Lowry theory of acids and bases. Okay, so first of all, we need to understand that an acid is a proton donor and a base is a proton acceptor based on the Bronsted theory of acids and bases. Okay, so when there is an acid-base reaction taking place, it actually involved the transfer of a proton from the acid to the base. Okay, solely by this definition. So if we are going to look at this particular system where you have ethanoic acids, so this is ethanoic acids, and you dissolve it in water, and most of you would have learned in secondary school that ethanoic acid is a weak acid, so it will partially ionize in water to give you ethanoics, which is what we call the conjugate base. And of course, in this case, H2O accepts a proton, in this case H plus, from ethanoic acid to give H3O plus. So we call H3O plus the conjugate acid. Okay, so if you look at the terms here, is actually arbitrary. Okay, so what do I mean by arbitrary? Okay, so if we are looking at a reaction going from left to right, in this case, ethanoic acid is actually the acid which give water the proton. So we will call ethanoic acid the acid here, of course, and then water the base. Yeah, but after ethanoic acid gives a H plus to water, it actually becomes a base because the negatively charged species, or the negatively charged center, is actually located largely at the oxygen. So if you remember the structure for ethanoic, it will look something like this. Yeah, of course there's a lone pair here. So the lone pair can actually accept H plus from H3O plus to give you back ethanoic acid. And that is why this particular system is in equilibrium. And that is why this whole topic is known as acid-base equilibrium. Because we are interested in when we dissolve a certain concentration of ethanoic acid in water, how much of it does it ionize, or how much of it does it dissociate. Okay, so we are going to use the term dissociation and ionization interchangeably because both terms are correct in describing the situations. Okay, we will not go into details. Like for example, in this case, you will know that ethanoic is what we call resonance stabilized, based on what you learned in organic chemistry. Okay, so because for the ethanoic anion, you know that the oxygen pi bond is what I've shown you in red over here, and then of course the O minus, you will have a lone pair of electrons that can overlap continuously with the C double bond O. Okay, so we will not discuss too much about this because this will be covered in the other organic chemistry topics. Yeah, so for this particular topic, we are solely interested in understanding the amounts which ionize, and then perform some calculation. And of course, the bulk of the topic later on is actually on buffer solutions and titration curves, and then determining the pH of buffers, etc. Yeah, but before you learn all those, stuff, you need to be comfortable in identifying what exactly is an acid and what exactly is a base. And then when an acid ionizes or give the base the H+, it becomes the conjugate base. And then when the original base accepts the H+, it becomes what we call the conjugate acid. Okay, then in this case, if I may just erase this portion, right, you can actually view this reaction using arrow pushing. So I'm going to just write it out over here. So we have ethanoic acids, okay, over here, and then the O will take on a partial negative charge, the hydrogen partial positive charged. The water here has a lone pairs of electrons, okay, over here. Yep, and then this oxygen will be partial negative charge, and then the H partial positive charged. Okay, I think from here you can understand that the transfer of the H+ to the O involve the lone pairs of electrons attacking the H, and then in this case it caused the heterolytic cleavage of the OH bond. Yeah, so the electron, the bonding electron pair is now being pushed towards the oxygen center, or you can say that it breaks towards the oxygen center. And in this case, after the reaction, so if I may just represent it with this arrow, yeah, so after the reaction, you are going to get something like this with a O minus. Okay, and then of course there's the lone pairs over here. So this lone pair, it actually comes from the heterolytic cleavage of the OH bond. Yeah, but for those of you who are sharp enough, right, you also notice that originally it already has two lone pairs. Yeah, so after the lone pairs, after the heterolytic cleavage, right, it doesn't really matter which lone pair we are talking about, because they are, you can't really distinguish them. Okay, and then after that you're going to get H3+, so you're going to get a OH here, and then an extra H, and then with a plus charge at the oxygen. Yeah, those of you who are familiar with formal charge, yeah, so this plus is a full charge as well as a formal charge at the oxygen. Okay, then of course you will also notice that for this particular system, because the ethanoate is a conjugate base, yeah, so the lone pair will also abstract a H+ back from H3+, otherwise known as the conjugate acid, and then now the OH bond will undergo heterolytic cleavage and break towards the oxygen, and in this case it will neutralize the charge, and then I will get back ethanoic acid and H2O. Yeah, so where the position of equilibrium will lie towards largely depends on which acid is stronger and which base is stronger. Okay, so in short, we are actually saying that is ethanoic acid a stronger acid, or is H3O+ a stronger acid? Okay, and is H2O a stronger base, or is CH3CO2- a stronger base? Yeah, and this whole topic, along the way, we are really trying to decide which is stronger and which is weaker, and then we need some numbers to guide us, and that is why along the way you learn things like Ka. We are going to introduce you to a new equilibrium constant like Ka for acids, and then Kb for bases, etc, etc. Okay, of course, those of you who are already quite familiar, I think you should be able to tell that H3O+ is obviously a stronger acid than ethanoic acid. Yeah, and that is why ethanoic acid is actually a weak acid, and the position of equilibrium actually lies towards the acid side. I mean the ethanoic acid side. Okay, and it has a relatively small Ka value in the region of 10 to the power -5. Yeah, and those of you in secondary school, you might be familiar that the amount of ethanoic acid which ionizes is maybe around less than 1%. Okay, yeah, and I'm just going to move on from here. Yeah, of course, another term which you need to be familiar with is what we call the conjugate acid-base pair. Yeah, so once ethanoic acid loses a proton, it will form ethanoate. So we will say that ethanoic acid and ethanoate forms a conjugate acid-base pair. Okay, and at the same time, H2O and H3+ also forms a conjugate acid-base pair. Yeah, so basically conjugate acid-base pair differ by a H+. Okay, yeah, this is something generic. I don't think I need to go into details, so do flag out if you don't really understand this, because I think I've used the example above to illustrate this portion relatively well. Okay, so I will just straight and go into exercise 1.1. So in exercise 1.1, you are supposed to identify the conjugate acid-base pair in each of the following reactions. Yeah, so over here, for the first question, we have nitric acid and ammonia reacting to give us nitrates and ammonium. And in this case, you notice that nitric acid loses a H plus to ammonia. Yeah. So in this case, we will call nitric acid the acid. And of course, after nitric acid loses the H plus, it forms nitrate. We will call nitrate the conjugate base. Okay, and in our case here, ammonia accepts the proton, so we will call ammonia the base. And then after it forms ammonium, we'll call this the conjugate acid. Yep. And then for question 2, the same thing. Ammonia reacting with H2O and in the process form ammonium again. So yep, so ammonia accepts a H plus from H2O, so we will call ammonia the base over here. And because H2O loses a proton, so we will call H2O the acid. Okay, and of course ammonium is now the conjugate acid, and OH minus is now the conjugate base. Yeah, so do take note that whether something is a conjugate acid of a base, or whether something is a conjugate base of an acid, it really depends on the partner which you are referring to. Yeah, so remember that in any equations, our focus is the forward reaction, which is from left to right. Okay, so if we are to reverse the reaction, so for example, the first question, right, if we are to reverse the reaction, so let me just erase this portion for simplicity. Okay, so if we are to reverse the reaction, then we will refer ammonium to be the acid here, because it loses a H plus to nitrates. Yep. Okay, so now if we reverse the reaction, okay, so do take note of it, don't listen to it halfway, huh? Okay, so if we reverse the reaction, yep, ammonium will now be called the acid, and of course ammonia here will be called the conjugate base. And then nitrate gains a proton from ammonium, so nitrate will be called a base, and nitric acid will be called the conjugate acid. Yeah, so it's a perspective thing. There is no absolute, it depends on your reference point, so that is something very important which you need to take note of. Okay, then moving on to 1.2, where we'll be discussing strong and weak acids and bases. So as what you may have already know in secondary school, a strong Bronsted acid is one which dissociates or ionizes completely in water to give H3O plus. Okay, so this term dissociates and or ionizes is important terms which you need to use in your answer. Yeah, but of course we underline the term completely, because the complete dissociation or the complete ionization is a key criteria for deciding whether something is a strong or weak acid. Yeah, and for the purpose of our discussion, in most of our discussion related to H2 acid-base equilibrium, we are dealing with the acids dissolving in water. So that's why you notice this particular portion where they said ionizes or dissociates completely in water to give H3O plus. And when we have H3O plus over here, you might be wondering why is it not H plus but H3O plus. Well, you might be aware that H plus essentially is a proton, so it's actually not very stable. Actually, it's not stable at all. Yeah. So of course we use H plus as a proxy for us to discuss a representation of an acid. Yeah, but scientists have of course discovered over the years that H plus is not the reality, so it doesn't really represent the reality. So in most cases, when we are dealing with acid-base equilibrium, we would like a H plus to be donated, or to be, in this case, stabilized by a water molecule. So in the process, it forms H3O plus. Yeah. But scientists have actually uncovered that it is actually more complicated than just H3O plus. Yeah. It could be H3O plus but stabilized by another water molecules or another two water molecules. So you can have species like H5O2 plus or H7O3 plus, and so on and so on. So it's actually very complicated, but in most cases when we are performing calculation, we will try to simplify the equation. Yep. So if you are wondering whether you can continue to use H plus, I think that should be fine in most cases. Yeah, but just be aware that H3O plus might be something which you see more common, especially in the topic on acid-base equilibrium. Yeah, even in advanced chemistry texts at the university level, or even at the graduate level, they tend to use H3O plus. But of course, when they use that at that level, they look into slightly different things lah. Yeah. There's a difference between diluted solution and concentrated solution because the properties can be very different. Yeah. So for acid-base equilibrium, for the purpose of our discussion for H2, we also tend to just focus on dilute solution. Yeah, because as the solution becomes concentrated, then they display slightly different behavior. But you will not encounter them very much in H2. Okay, yep. So so in this case, there are certain bullet points which you need to be aware of. Like for example, the conjugate base of a strong acid has a low tendency to accept a proton back. Yeah, so in that case, I think it will be plain to notice that if I have a strong acid here, which ionizes completely in water to give H3O plus, I will not expect chloride to abstract H plus back from H3O plus to give me HCl. Yeah, because HCl aqueous on its own, right? It doesn't exist. I mean, it doesn't exist as molecular HCl. So meaning when we are looking at this, we are not looking at this form in water. So this is not the form that exists in water. So what exists in water is actually chloride and H3O plus. Yeah, so that is the reality. Yeah. And that is why I focus on telling you that the solution must be diluted, because for concentrated solution, you do get some molecular HCl floating around, and then maybe it will exist in the airspace above the concentrated solution, and things will get really complicated. Yeah, so yeah, I mean, without going to very complicated things, we let us just focus on dilute solutions. Okay, so in dilute solution, you will not get molecular HCl. Yeah, please understand the term whenever we try to say, let's say molecular ammonia, molecular HCl in aqueous solution. Yeah, so molecular ammonia exists in aqueous solution as well as molecular ethanoic acid, because these are weak bases and weak acids, so they do not ionize completely. Yeah, and that's why the bulk of them exist as the molecular form. But for HCl being a strong acid, ionizes completely, you will not see any molecules of HCl around. And it is the same for the rest of the strong acids like nitric acid, HBr, HI, etc., etc. Okay, yeah. So in contrast, a weak Bronsted acid will ionize partially, or you can say dissociates partially. So the term partially and completely will be important for us to recognize that indeed you understand the difference between a strong and a weak acid. Yeah, and of course the question is how partially is partially, how completely is completely. Yeah, normally in a standard H2 kind of questions which you will get in exam, normally when we are talking about weak acid, you are going to get a Ka value of the magnitude, say 10 to the power of minus 3 or lower. Yeah, so and that's why it is safe for you to say that these are relatively weak acid. But sometimes you will hear your tutor saying, oh, this is a strong weak acid. So what exactly is a strong weak acid? Yeah, so okay, so weak acid in this case is the noun. Yeah, so we are talking about weak acid that is relatively strong because the Ka value is not very low, but not very high. Yeah, and in that case, you will know that when you are trying to make approximation, later on we are going to do some calculation, you realize that if you are trying to make some approximation, it will not come across as very accurate. Okay, yeah, so be aware of the double-headed equilibrium arrow. So it's like this. I think in chemical equilibrium we emphasize this, right? Never write your arrow like this, because this represents resonance. Okay, so this is incorrect. So you should not be writing a double arrowhead. Okay, yeah. Moving on, a strong Bronsted base, in this case, will ionize completely as well. So in this case, strong Bronsted base, they tend to be ionic compound, like sodium hydroxide solids or potassium hydroxide. So when you dissolve them in water, they do not exist as the solid anymore. So you are just going to get a solution full of sodium plus and OH minus. Okay. On the other hand, for weak Bronsted bases, they tend to be molecular form. If you learn more organic chem, you notice that they tend to be amine based. Yeah, so ammonia is not an amine, so ammonia is ammonia. But when I mean amine based, I mean, like, for example, one of the H in ammonia is being replaced by an LQ group. So let's say it's an R group. Okay, so maybe I use a very specific example, methylamine. Yeah, so methylamine is an example of an amine, and because of the lone pairs on N here, so the lone pairs of electrons have the tendency to abstract a H plus from the solution. So therefore, methylamine is a weak base, or we call it a weak Bronsted base. Okay, so there are other examples which you're going to deal with them as you move on in your organic chemistry education. Okay, so remember that the strength of an acid is not the same as the concentration. Okay, so you can have a very concentrated weak acid, but it is still a weak acid because it doesn't ionize completely in water. Okay, let's move on to exercise 1.2, where you are supposed to match each acid on the left with the correct descriptors on the right. Okay, so we have a very dilute nitric acid. So nitric acid, as we discussed earlier on, is a strong acid. So therefore is a dilute but a strong acid. Okay, so dilute and strong acid. So we match these two. Ethanoic acid at 4 moles per dm cube, pretty concentrated. Yeah, so ethanoic acid is a weak acid, but this concentration is quite high, so it's concentrated, so it's a concentrated weak acid. Okay, this is a very dilute weak acid, so it's a dilute and weak acid. Okay, so do take note that there's a difference between something that is concentrated and its strength. It's very important for you to distinguish that. Okay, so without further ado, we'll move on to topic 2 on calculations involving acids and bases. As what you might have remembered from the earlier chemical equilibrium and solubility product topic, any equilibrium calculation, you can use an ICE table to actually help you in terms of visualization to work through the problems. Yeah, so I would really suggest using ICE table to help you. But of course, after a while, you realize that for acid-base equilibrium, the variable tends to be quite similar. So you might not feel that the ICE table is required. Yeah, but of course, before that, we need to define what we meant by pH and pOH. Basically, when you put a P in front of either the H or the OH or even Kas, we are taking the negative log to the base 10. So basically, pH simply means negative log to the base 10 concentration of H plus in the solution. Okay, and so therefore, if you do a little bit of manipulation, you will realize that the concentration of H plus is just 10 to the power of minus pH. But you do not need to memorize this, so don't memorize. These are things that you can work through with your mathematics. Okay, so same idea goes for pOH, so I will not elaborate. Okay, 2.2, we will introduce you to an idea of the auto-ionization of water under standard conditions. Yeah, so pure water does conduct electricity slightly because they auto-ionize. So auto-ionize, you can replace this word with self-ionization. So it's a very slight ionization. So that means that itself act as the base and itself act as the acid. So they transfer a proton to one another, or rather from one party to the other party. So one will get H3O, become H3O plus, the other become OH minus. So this is known as auto-ionization. Okay. The simpler way, of course, is just to look at H2O, which involve the heterolytic fission or the heterolytic breakage of the OH sigma bond, and in our case to give H plus and OH minus. Yeah. So in terms of organic chemistry, because most of you, if not all of you, hopefully remember some stuff you learned from organic chemistry. So this arrow pushing actually goes from the OH sigma bond, you push towards the O here. Yeah, so in the process you will get a H plus. Okay, and then of course originally I have two lone pairs. After you push to the O, then the OH minus at the O there will get an extra lone pair. I will represent with yellow. Okay, so it will be a negative charge. Okay, so in this case, the equilibrium constant, as you have seen here, this is indeed an equilibrium. So we can actually write out an equilibrium constant Kc, where H plus OH minus divided by H2O. And as you know, H2O has a concentration of about 55.8 or 5.6 moles per dm cube, being a constant. It will not be reflected as well. So if you bring this across, you get a constant term. Yeah, so this particular constant term, we call it Kw. Yeah, so Kw is known as the ionic product of water. Yeah, and as per all equilibrium constants, only dependent on temperature. So it's a temperature dependent variable. And as you might be aware, the breaking of the OH bond, I mean, it's solely, I won't say it's solely, but largely results in the formation of H plus and OH minus. Yeah, so the auto-ionization of water in this case, you would expect it to be endothermic. Yeah, so therefore, the higher the temperature, you expect the position of equilibrium to lie more to the right, and therefore you expect the value of Kw to increase as well. Okay, yeah, so there is a need for you to do some very simple manipulation. Again, please do not commit to memory, because if you try to commit to memory, then you realize that the learning of this topic is no longer interesting. Yeah, so you need to be very comfortable in converting from Kw to pKw. In fact, throughout this whole acid-base equilibrium. So for example, from Ka to pKa expression. Okay, so you need to work a little bit on your mathematics as well. So basically you are taking a negative log base 10 on both sides, and then because this is multiplication, so it becomes a plus, and then because we define negative log base 10 of H plus as pH, so this is essentially pH plus POH. Okay, yeah, I know this is straightforward, but you know, sometimes when it comes to exams, under exam pressure, or when you're doing your tutorials, you might forget. Yeah, so these are something which you need to take note of as well. Okay, yeah, then moving on to 2.3, relationship between H plus, OH minus, and pH. Yep. If you have heard me earlier on, okay, so some of the things I'm going to mention here, I think will be obvious to some of you. Okay, so as I said to you earlier on, and it also appears in your data booklet, at 25 degrees Celsius standard condition, Kw is 10 to the power minus 14. Okay, so this value is also given in the data booklet, so you need to know, it's actually on the second page. Okay, so therefore when you express it, pKw is equals to pH plus POH, and this is equals to 14. Yeah, and that is why for solution that is neutral at 25 degrees Celsius, we say that is pH 7. Okay, but this is not true when you change the temperature. Okay, so when I change the temperature, the neutrality pH value can change. Okay, so maybe when we are close to boiling point of water, maybe the neutrality pH is about 6.5. But that doesn't mean that water is acidic. Okay, the reason is when we increase the temperature, we are encouraging the ionization of H2O. But when we are encouraging the ionization of H2O, right, in the process, we are forming the same amount of H plus and OH minus. So therefore, the concentration of H plus and OH minus balances off each other. So we are still dealing with a neutral solution. Yeah, we are only dealing with an acidic solution if there is an imbalance of either party. So if we have more H plus than OH minus, we get an acidic solution. If we have more OH minus than H plus, we get an alkaline solution, and so and so forth. Okay, so that is something you need to be aware of and confident with. Yeah, and this is also something which student tends to make mistake in exams, because sometimes we'll change the condition. We'll tell you that maybe at say 80 degrees Celsius, the pKw is 13, for example, and then therefore pH is 6.5. So some students will think that the solution is acidic, which is not true. Okay, so remember that similar to Kc, Kp, and Ksp, okay, similar to Ksp, Kc, and Kp, equilibrium constants, these are all temperature dependent variable. Okay, so Kw, Ka, later on you're going to meet Ka and Kb, all this, they will change, the value will change according to temperature. Okay, so I think we have a table over here which I think showcase to you the different values of the concentration of H plus. So I will not go into details. If you want, you can calculate the pKw yourself. Okay, so we have an exercise 2.1 over here, and with reference to the above data on Kw, state whether the following statements are true or false. Okay, so ionic dissociation is an endothermic process. Yes, this is obviously true. How do we tell? Number one is by logic. What do I mean by logic? Earlier on, I mentioned that the only way you can get H plus and OH minus is by the heterolytic cleavage of the OH bond. So this is largely bond breaking. So if it's largely bond breaking, I'm going to expect the reaction to be endothermic. But of course, you can argue that water on its own, they are stabilized by hydrogen bonds. Yeah. So technically, you should also consider the interaction between the water molecules and water molecules, as well as the water molecules and H plus and the water molecules and OH minus, before you can be before you are confident to say that this is an endothermic process. Yeah. So we are making an assumption that the interactions more or less don't change too much, and that's why we can we are confident that it's an endothermic process. But of course, talk is cheap, so we need to look at data. So you notice that as the temperature increases, the value of Kw increases as well. Yeah, so therefore from this particular evidence, the ionic ionization, or the self-ionization of water, the self-dissociation of water, is an endothermic process. Okay, then for 2 and 3, as water is heated up, concentration of H plus and OH minus increases. You notice that these two statements did not say the other party. So I hope you can understand that when concentration of H plus increase, concentration of OH minus will increase accordingly as well. So 2 and 3 are tied to each other. Remember that they are tied to each other. It cannot be H plus increases more than OH minus and suddenly the solution becomes acidic. So this is incorrect. Okay, part 4. In pure water, the concentration of H plus is higher than OH minus at 60 degrees Celsius. This is nonsense, because pure water, H plus concentration should be the same as OH minus concentration. Okay, part 5, water remains a neutral liquid at 60 degrees Celsius. So of course this is correct. I think we emphasized that quite a bit just now, because the concentration of H plus and OH minus are the same. And then for part 6, the pH of pure water at temperature greater than 25 degrees Celsius is 7. This is incorrect. It should get lower because of the increase in ionization of H2O. So you get a higher H plus and OH minus concentration. You take a negative log of them, you get a value below 7. Okay, when in doubt, you can just punch your calculator and verify. Okay, Then moving on to 2.4 over here, right? We have the pH of strong acid and strong base solution. Okay, this is not very inspiring because basically the concentration of H plus is the same as the concentration of the strong acids in a dilute solution. I always like to emphasize to students is in a dilute solution, because for a concentrated solution things can get tricky. Yeah, but I think you can take that off the equation for H2, because I think in H2 we will not tend to go into complicated stuff like asking you to calculate things involving concentrated strong acid or even concentrated weak acid. When I mean concentrated here, I really mean very concentrated. Yeah, because that really involves a totally different ball game. Okay, yeah. Then if the concentration of acid or base is 10 to the power minus 7 or lower, I think this is important. We need to incorporate the auto-ionization of water in our calculations. Okay, so you have to take them into consideration in your calculations. Okay, then some of you might be asking, then why is it that if the concentration of the acid is bigger than 10 to the power minus 7, we don't need to include the auto-ionization of the water molecules? That is because you just imagine that, let's say you add 10 to the power minus 7 to say 10 to the power minus 3, the numbers is actually very close to 10 to the power minus 3. Okay, so it the 10 to the power minus 7 becomes relatively insignificant. That's the reasons. Okay, yep. Then I think we'll just start off with exercise 2.2 to warm up a little bit. So we have an aqueous solution containing 1.0 times 10 to the power 5 moles per dm cube of HI, which is a strong acid. Okay, so your job is to calculate the concentration of H plus in moles per dm cube, and then hence the pH of the solution. Okay, so as what you have seen earlier on, concentration of HI will be the same as the concentration of H plus, because HI is a strong acid which ionizes completely, and therefore the concentration will be 10 to the power minus 5 moles per dm cube. Okay, and pH is simply just minus log base 10 of 10 to the power minus 5. Okay, and we will get 5.00. Okay, so we are getting pH 5 over here. Okay, so it's a straightforward calculation. And then for question 2, an aqueous solution containing 0.01 moles per dm cube of barium hydroxide. Take note that this is a diacidic base, so one equivalent of barium hydroxide gives you 2 equivalent of OH minus. Okay, and then I mix with 0.05 moles per dm cube of KOH. Okay, and then of course my job is to calculate the pH of this solution. Okay, so over here we need to look at the total concentration of OH minus, so we need to look at OH minus total. Yeah, so that will be the contribution from barium hydroxide, which is a diacidic base, so we need to multiply 0.010 by 2. Okay, and then we need to add this to 0.050. Okay, you take note from the way the question is phrased, they are not mixing two solutions together. So the solution itself already contains 0.01 mole per dm cube of barium hydroxide and 0.050 moles per dm cube of KOH. So there isn't a need for you to do anything with the volume term. Yeah, so if you add the two up, you are going to get the total OH minus concentration to be 0.070 moles per dm cube over here. Okay, and then therefore we can easily calculate POH, which is simply minus log base 10 concentration of OH minus. Okay, so if you punch your calculator, you should get around 1.15. Okay, and then we can easily calculate pH over here. That is 14 minus POH, and then we should get 12.8. Okay. Yep. Then we have question 3. Aqueous solution contains 1 times 10 to the power minus 8 moles per dm cube of nitric acid. Yeah. So in this case, the student might simply just say that the concentration of H plus is equals to 10 to the power minus 8 moles per dm cube. Yep, and then after that, the student will simply calculate pH and then just minus log base 10 and 8. And then the students will just happily submit this as the answer, but this is actually not correct. Yeah, because for a aqueous solution at 25 degrees Celsius, pH cannot exceed 7 because that will mean that there's an imbalance of OH minus against H plus. Yeah, so in that case, why is this incorrect? Yeah, because when you are performing this calculation, because the concentration of H plus from the strong acid is less than 10 to the power minus 7, you have to incorporate the auto ionization of water in your summation, okay, of concentration of H plus. So in this case, there is a missing part over here, so we have to add 10 to the power minus 7 here, and then it gives us 1.1 times 10 to the power minus 7 moles per dm cube. And then when we calculate pH, punch the calculator, we should get 6.96. Okay, yeah, those students at this stage, right, if you are sharp enough, you might recognize that a simple addition like this is actually conceptually incorrect. Okay, so this is kind of conceptually incorrect, but it is a good proxy. Okay, it is a good proxy. Why is it conceptually incorrect? Because the ionization of water, in this case 10 to the power minus 7, right, and the presence of the strong acid, which is nitric acid, right, will affect the auto ionization of water. Yeah, okay, because when we are looking at the auto ionization of water, there is no excess of H plus or OH minus that will shift the position of equilibrium. Am I right to say that? Yeah, so because of that, we can simply just take 10 to the power minus 7 and then calculate the pH. But when the system already have nitric acid, we are kind of dealing with a common ion, but we are not talking about salts here. I hope you see the difference. We're not talking about salts not dissolving, but yeah, so we have a H plus in the system, so it will affect the auto ionization of water. Yeah, so it will actually suppresses the auto ionization of water by a little bit. So you are expecting less contribution from H2O ionization. Yeah, so the actual value, if you incorporate that in your calculation, you should be getting about 6.98. But of course, to do that, you need to learn a concept known as the systematic treatment of equilibrium, but that is not in the H2 curriculum, so you don't have to worry about that. Okay, yeah, so I repeat, whatever we are doing here is just a proxy, because it's conceptually incorrect to consider the two system independently, because whatever H plus in the system will affect one another. Okay, if you are confused, just think back about the KSP which you have done last year. Okay, if you're not so confused, I think it's okay. You can read up on the systematic treatment of equilibrium, and that will be very interesting. Okay, so with that, let us move on to exercise 2.3. Okay, then exercise 2.3, we have an aqueous solution contains 0.10 moles per dm cube calcium hydroxide. You are told that it's a strong base, okay, and then you're supposed to calculate the concentration of OH minus in moles per dm cube, and hence the pH at 25 degrees Celsius. Even if they don't tell you 25 degrees Celsius, you can assume that, okay, because it's kind of no choice. Okay, so again, we will use the same logic, because calcium hydroxide is actually a diacidic base. Yeah, so therefore the concentration of OH minus is simply 0.10 multiplied by 2. So I'm going to get 0.20 moles per dm cubed. So this is simply the concentration of OH minus being contributed by 0.1 moles per dm cube of calcium hydroxide. Okay, and then when we calculate POH, I'm just going to take negative log base 10 of this, and I'm going to get 0.699. Okay, and of course pH is simply 14 minus that, so I'm going to get 13.3. Okay, so this will be relatively straightforward. Okay, next we look at question 2 of exercise 2.3. over here we have solution X. Contains HCl, pH 2.2. I have another solution Y, same volume as X, okay, but my Y contains nitric acid, pH 1.6. I mix the two solutions together, calculate the pH of the final mixture. Okay, what most students will do is maybe they will take 2.2, 1.6, and then simply divide by 2, and then actually that is incorrect. Yeah. Because technically you have to calculate the H plus contribution or H plus concentration due to each of the solutions. Okay, so I'm going to calculate the total concentration of H plus, so total. Okay, this will be the contribution from HCl, which essentially is 10 to the power of minus 2.2. So for those of you who are a little bit confused by this, how come I can just take 10 to the power of minus 2.2, right? So remember that remember that pH is minus log base 10 concentration of H plus 2.2. So essentially I can shift the minus to the right, so I get minus 2.2. Then because it's log base 10, so H plus concentration is 10 to the power of minus 2.2. Yeah. So concentration of H plus due to HCl, concentration of H plus due to nitric acid, that is 1.6. And then because I mix the two solutions together and each of the solutions has the same volume, so that means that when volume doubles, concentration of half. Okay, and then from here I'm going to get if I punch my calculator, 0.0157 moles per dm cube. Okay, and then I will calculate my pH based on this concentration, which is minus log base 10 concentration of H plus. Okay, and then I'm going to get 1.80. Okay, yeah. So I hope you find the calculation not as tough as you think, but of course we haven't gone into calculating weak acids. Okay, so for 2.5, we are just going to get to the meat of the chapter. So we have we are going to define two variables: acid dissociation constant Ka and base dissociation constant Kb. Yeah, actually it's a little bit weird to say base dissociation constant, because the base actually do not dissociate, unlike I mean, weak base don't dissociate, weak base ionizes. The reason why weak base don't dissociate is because your weak bases are largely in molecular form. So when you put them into water, they cause the H2O to ionize in that sense, and in the process produces OH minus. The base itself forms the conjugate acid. So your base do not break up in that sense. So it's a bit weird to call it base dissociation constant, but it has some legacy issues. So we just keep it, but I think it's good to be aware why is it called base dissociation constant. Okay, then of course you have seen this in our starting portion when we are discussing ethanoic acids. Okay, then we have HA partially ionizes in water to give A minus and H3O plus. So over here we are going to write a Ka expression. Yeah, so that will be the equilibrium concentration of H plus or H3O plus for that matter, A minus divided by the equilibrium concentration of HA. Yeah, then you'll notice that the bigger the value of Ka, right, that means that the greater the extent of ionization. Yeah, and of course the bigger the value of Ka, the smaller will be the value of the pKa. Okay, so it has this inverse relationship. Again, no need to memorize. Once you are in doubt, just punch calculator and I think the answers will be quite obvious lah. So don't worry about all these little things. Do not memorize unnecessary things. Okay. In fact, this is the single most important equation you need to know throughout your studies for acid-base equilibrium. And this equation you actually don't have to memorize because it actually comes from here, and most of you can actually write this out. So in all honesty, acid-base equilibrium should be one of the easiest topic in chemistry, but I don't know, students somehow feel that it's the most difficult. Okay, that is why when you study this topic, it is important for you to focus on the fundamental understanding of the phenomenon rather than blindly memorizing equations. Okay, if you want to memorize, actually the only thing you might want to know is the relationship between pKa and Ka, or the relationship between P something and, and that something. And then of course, how to write Ka expression. Of course, that is not very difficult. Okay, so I'm going to move on. Base ionization constant, base dissociation constant. Okay, so base ionize partially in the process, give you the conjugate acid and OH minus. So again, you can write a Kb expression out. You can define pKb as well, and the greater the Kb value, the smaller the pKb. So same logic. So these are just some Kb values of the various bases. Okay, the relationship between Ka, Kb, and Kw. Okay, so there is a little bit of derivation here, and sometimes the students might not be very confident about what exactly is going on. So again, in the end, they will end up memorizing equations lah. Okay, so fret not. That's not supposed to be the way. Okay, so if I'm going to zoom into this, right? Remember earlier on that we say that we define this as the acid, okay, and of course when this is the acid, ethanoate becomes the conjugate base. Okay, so from here we can actually write out this particular Ka expression. Okay, but the conjugate base itself, right, being the base of a weak acid itself, is also a weak base, and therefore itself can also ionize in water, and in the process produces ethanoic acid and OH minus. Yeah, so over here we can also define a Kb expression. Yeah, so remember that whatever weak acid that ionizes, the base it produces can also ionize back, because the base it produces is also a weak base. Yeah, so what we're going to do here is we are attempting to combine the two equations. Okay, so we are multiplying Ka and Kb together, and you notice that when you multiply the two together, right, the numerator here, which is the ethanoate, will cancel out the denominator here, and then the denominator, which is ethanoic acid, will cancel out the numerator for Kb, and then eventually you're going to end up with Kw equals to concentration of H plus multiplied by concentration of OH minus. And then after that, when you expand this out, you notice that Ka times Kb equals to Kw. Okay, how do we get this? Because Ka and Kb equals to Kw from here. Okay, right? So that's how this thing is obtained. And then after that, when you take the negative log base 10 of negative log base 10 of the concept of Ka and Kb and then Kw on both sides, you end up with pKa plus pKb equals to pKw. Okay, yeah, so sometimes when students reach here, they get super confused because there seems to be more equations to memorize, but honestly, you do not need to really memorize this, because again, as I've shown you above, the logic is that for the same system, which means for the same conjugate acid base pair, you can allow the pK and pKb, adding them up together, which eventually will give you pKw, because essentially each of them is responsible for their own H plus and OH minus. Okay, that's not exactly the correct way of saying, but that is one way which you can look at things lah. Yeah, but as we have shown here, mathematically, this is how it works. Okay, then so this is a very important expression, because from this particular expression, you'll notice that if I give you the Ka of ethanoic acid, you can easily tell me the Kb of its conjugate base, which is ethanoate. So vice versa, if I give you the Kb of ethanoate, you can easily calculate and tell me the the Ka of ethanoic acid. Okay, so I know there's no example here, so maybe I will just illustrate with one simple example, which is an example I often use to discuss with students. So for example, ethanoic acids. Okay, ethanoic acids pKa is 4.76. Okay, I think if you are familiar with weak acids, this is one of them that you need to know off the top of your head. So pKa is 4.76. Yeah. Then what about ethanoates? What is the pKb? So if you truly understand this, you notice that it's simply 14 minus 4.76. So you are going to get 9.24. Okay. Now, is ethanoic acid a stronger acid? I mean, is ethanoic acid able to perform its role as an acid more prominently, or ethanoates being able to perform its role as the base more prominently? This is a difficult I won't say difficult, but this question might not give you might not have a very obvious answer. Yeah, but if you simply compare the pKa and pKb, you notice that the pKa is a lower value than the pKb. Yeah, so that is why you realize that the position of equilibrium actually lies a bit more to the right when we are looking at the ionization for ethanoic acids. So therefore, as an acid, ethanoic acid is a stronger acid than its corresponding conjugate base as a base. Yeah, so that's what the value is trying to tell you. Again, these are not things which you probably want to memorize. Along the way, as you grow, you'll be more familiar, and then you notice that it's not as difficult as it seems. But right now, I thought I just want to introduce to you some of these ideas. Okay, and then 2.6, we are looking at the extent of ionization, or the degree of dissociation. So basically, it's just the amount which ionized divided by the initial. Yeah, so we give it an alpha term. So if alpha is close to 1, that is a strong acid or base, because essentially the concentration of acid which ionizes or dissociates is the same as the initial concentration. So weak acid has an alpha much lesser than 1. Why are we telling you this? Sometimes the question might require you to calculate the fraction of ionization, and that is why we're introducing this to you. Next, we are moving on to section 2.7, where we are going to calculate the pH of weak acid or a weak base solution. Okay, so because they ionizes or dissociates partially, so the solution concentration for the H plus and OH minus will be lower than the initial concentration of the solution. Okay, so over here I will just use a relatively generic way of representing it. So suppose that we have a weak acid HA in aqueous solution, and then in water, which is the aqueous medium, it will ionize partially to give me H plus aqueous and A minus aqueous. As you have seen above, this is defined as Ka. Okay, so we can use the same method we use for chemical equilibrium. So we can create an ice table where the initial concentration, so it will be good to put the units here as what we mentioned in chemical equilibrium, because if you put the short form ICE, you may not know whether they are referring to initial concentration or initial number of moles. Of course, for acid-base equilibrium, usually we are looking at initial concentration. Okay, we rarely work in terms of moles. Yep. Okay, so over here we can have the initial concentration of C naught. Okay, and of course we don't deal with water because its concentration is constant, being way higher than that of the rest of species. Okay, and then H plus and A minus 0 initially. Okay, so the change, again we let the change be minus X. Okay, similar to chemical equilibrium. Then we have plus X here. So the equilibrium concentration of HA will be C naught minus X, and then the equilibrium concentration of H plus will be X moles per dm cube and A minus X moles per dm cube. So similar to chemical equilibrium, we define Ka to be the concentration of H plus A minus together, so that will be X squared over the initial concentration, the equilibrium concentration of HA, so that will be C naught minus X. Usually, to simplify our calculation, we will make an assumption here. We will assume that the ionization is negligible as compared to the initial concentration. So that will mean that we will assume C naught to be way greater than X. Yeah, so because of that, we'll be able to get Ka equals to X squared over C naught, and then we'll be able to get X squared equals to C naught multiplied by Ka, and then we can get X to be equals to the square root of C naught multiplied by Ka. This is the expression that a lot of guidebook and even textbook wrote for students, and students thought that they actually need to memorize it. Yeah, so again, my suggestion is I prefer the students to work from first principle. So create an ICE table. It doesn't take you too much time, and then formulate the actual Ka expression, and then know what kind of assumption you are making. And then from there, you will be able to calculate X easily. And then, as you know, X is the equilibrium concentration of H plus. You take the negative log to the base 10 of X, and then you will get the pH. Okay, so in general, this is the way you should go about working through the problems. Okay, so again, you have exercise 2.4 here, which is a work example for you. Okay, so although the answer is given to you, so let me just run you through. So again, first you need to find the pH and the degree of dissociation. So this is the alpha, which we mentioned earlier on at the end of section 2.6. Okay, so this is the alpha here. Yep, and then you are given the K of ethanoic acid to be 1.8 times 10 to the power minus 5. So you can see from the ICE table that the units is not written. So as I mentioned, it will be good to write it in. So please write in the units. Okay. And then, yeah, so you formulate the ICE table to be like this, and then you can write the K expression. So again, this is the assumption we make here. So when you work from first principle, you will be able to get X equals to 1.34 times 10 to the power minus 3, and then pH to be 2.87. The reason why we ask you all to make the assumption that X is much lesser than the initial concentration for H2 is because somewhere in your curriculum it was mentioned that the solving of quadratic equation is not required for the solving related to acid-base equilibrium. So let me just show you this relevant parts in your syllabus document. Yeah, so under your syllabus document, acid-base equilibrium is under topic 10. If you scroll down under learning objective 10C, it's written over here that the calculation of H plus concentration and pH values of strong acid, weak monobasic monoprotic acids, strong bases, and weak monobasic acids. And then there's a bracket component here. It reads, calculations involving weak acids, bases will not require the solving of quadratic equation. Yeah, so because of this, it will be good if you can make an assumption that X is much lesser than the initial concentration, and then after that you can solve it in an easier fashion. But of course, if you choose to do quadratic equation, we cannot stop you. Yeah, it's just that it might not be advisable because you will be penalizing yourself in exam. Yeah, then some of you might be asking, is this assumption always true? If you remember what I mentioned earlier on, it is not always true. The reason is because if your Ka is of a relatively large magnitude, say 10 to the power minus 2, or even in the low 10 to the power minus, or rather in the high 10 to the power minus 3, right, you might get a relatively different answer if you make an assumption. Yeah, but for the purpose of H2, we will just ignore that. But as I said, if you wish to solve quadratic equation, you can go ahead, but again, penalizing yourself in the process. Okay, yeah, then yeah, whatever I mentioned, I think is given in this particular note over here. And if you remember from the question, you're supposed to calculate the degree of dissociation, so that will be the X. So we will take X value 1.34 times 10 to the power minus 3 divided by 0.1 multiplied by 100%. Yeah, so that's about 1.34% dissociated. Yeah, so I guess the assumption is still quite valid. Yeah, so moving on, we'll move on to exercise 2.5, where you're supposed to calculate the pH and the degree of dissociation of a solution of a certain concentration of aqueous ammonia. So again, instead of Ka, we are looking at Kb for now. So we'll work using the same method. So we have aqueous ammonia. ionizes partially in the presence of H2O. Okay, in the process, it gives us the conjugate acid ammonium, and then OH minus. So again, I stable. So have the habit of writing the concentration term, okay, over here, so that you know what you're dealing with. And then initial concentration is given to be 0.125, so that's 0.125. So the rest will be dash, and then the extent of ionization we are not sure, so we let it be y. So minus y plus y plus y. We are defining Kb over here, so it's good to write this at the top of the equilibrium arrow. And then the equilibrium concentration of ammonia will be 0.125 minus y, and then ammonium will be y and y. So again, over here we will define Kb to be y squared over 0.125 minus y. Yeah, and over here we are going to make the assumptions. So we are going to assume that the concentration of the initial concentration of ammonia is way greater than the extent of ionization. Then so therefore my Kb is equals to y squared over 0.125. Okay, and then I'm supposed to calculate the pH. So I'm given a Kb value, that's 1.78 times 10 to the power minus 5. So 1.78 times 10 to the power of minus 5 multiplied by 0.125. I'll take the square root, and this is equals to y. Okay, so now I'll just punch calculator. I should be able to get y to be 1.49 times 10 to the power of minus 3 moles per dm cube. Okay, but take note that y is actually the concentration of OH minus. So if you take the negative log base 10, you are calculating POH, not pH. So just be careful. So minus log base 10, 1.49 times 10 to the power minus 3, we will be able to get 2.83. Okay, so POH 2.83, pH would be 14 minus 2.83, and we'll get 11.2. Okay, and then to calculate the extent or the degree of dissociation, we'll take y divided by 0.125. Okay, so I'll just do the work, write the working over here. So degree of dissociation would be equals to 0. Sorry, not 0. Would be, where is it? 1.49 times 10 to the power minus 3 divided by 0.125 multiplied by 100%. So I'm going to get 1.19% as the degree of dissociation. Okay, so the way to work out exercise 2.5 is very similar to exercise 2.4. So if at this point in time you have some issues, please go back and review them, because it is highly necessary that you are comfortable in working through the basics of at least finding out the initial concentration of a weak base and a weak acid. Okay, so that is exercise 2.4 and 2.5. Okay, and then we have a work example, exercise 2.6. So over here we have a stimulant, caffeine, which is a weak base. So you need to read the question very carefully so that you know whether they are dealing with weak base or weak acids. Okay, so we have a weak base over here which ionizes again partially to give us the conjugate acid and OH minus. And then we were told that a certain concentration of caffeine has a certain pH. And then right now there are two parts to this question. We're supposed to write down the Kb expression, and then after that calculate its value at 25 degrees Celsius. Okay, so this shouldn't be too difficult. So again, the Kb expression, we have written it out, and then we are given the pH of this solution, which is 11.5. So if you are sharp enough, I mean, if I may just make life a little bit easier by just roughly writing down the ice table. Yeah, but so I'll just write it on the right hand side. Okay, so normally we will let the weak base be something like A, okay, then plus H2O, and then we equilibrate to give us AH plus, okay, maybe not A, because A seems to imply that it's an acid, so let let me represent it with B then. Okay, so BH plus plus OH minus. So again, because the working here straight away jump into the action, so I thought I'll create an ice table for you to see in a clearer fashion. Okay, so we have initial concentration 0.020, so dash dash dash, and then we're looking at minus x here plus x, and then 0.020 minus x, and then we have x and x. Do take note that you are aware of the pH of the solution. Okay, it's unlike earlier on when you are supposed to calculate Kb, or rather you're supposed to calculate the pH. So yeah, you are given the pH of the solution. So from the pH you can determine pOH, which is what they are doing here, and then from pOH you can actually determine the concentration of OH minus, which is essentially the X. Yeah, so over here they determine the concentration of OH minus, and then they work out the Kb expression over here, which essentially comes from what I've written above. So essentially the Kb expression is x squared over 0.020 minus x. You notice that the x has already been calculated out for you. Okay, as what I mentioned earlier on, because it's given to us indirectly. Yeah, so we're just going to substitute in, and then we should be able to get a Kb value over here. So yeah, it's given to be this. For those of you with a sharp pairs of eyes, right, you notice that over here the minus x is included. Yeah, you do not make an assumption and you just ignore it. Yeah, the reason is I mean, it's just a very lame reason, because you're not solving quadratic equation here, so it's actually totally fine for you to include that in, because it's not too difficult for calculation anyway. Okay, so over here you shouldn't make this assumption. Okay, then of course to calculate the degree of dissociation, again, it's not very inspiring. I think most of you should be able to do that. Yeah, okay, so we'll just straight away move on to exercise 2.7. We have a pH of a weak acid, HA, concentration of this, and then pH was found to be 3.0. Calculate the Ka and pKa of the weak acids. Yeah, so this wouldn't be too difficult. Okay, so we're going to use the same logic. Okay, so we have HA plus H2O ionized to give us H3O plus A minus. Okay, so we have the ice table here. My apologies that I'm not going to write down the units because I need to work it out fast. Okay, yeah, and also to save space. So initial concentration 0.100, amount H2O is dash dash dashed, and then okay, technically this is minus x plus x plus x. Okay, I'm just going to do it a little bit differently, so I want to see whether you can catch what I'm doing. Okay, so for those of you who are already very sharp and you kind of like know what's going on, you might be aware that actually x is already given to you indirectly because the pH is 3.0. Yeah, so for those of you who are really sharp, you actually do not need to put in minus x plus x plus x. You can just straight away put in the value. So essentially this is minus 10 to the power minus 3.0. Okay, 10 to the power minus 3, 10 to the power minus 3. So this will be 0.100 minus 10 to the power minus 3.0. So 10 to the power minus 3.0, 10 to the power minus 3.0. Okay, so if you are sharp enough, you can do that relatively quickly. Then so from here, Ka will be just 10 to the power minus 3.0 squared over 0.100 minus 10 to the power minus 3.0. Okay, punch your calculator, you should be able to get 1.01 times 10 to the power minus 5 moles per dm cube. Yeah, and then from here, pKa can be obtained quite easily. Basically, pKa is just the negative log base 10 of the Ka value, so that's 1.01 times 10 to the power minus 5, and then I will be able to get 5.00. Okay, so I hope the calculation isn't too daunting, and as long as you're systematic with your approach, you should be able to get the answers relatively easily. Yeah, yeah. Usually the students, based on your seniors, experience, the main problem comes later on. Not in front. Yeah, and after a while they get confused with what they learn in front, and that's where the problem comes. Okay, so right now we have the strength of acids and bases that will be under section 2.8, Yeah, so we have a few bullet points here. So strength of acids, measure how readily it donates the protons. Then dependent on structure, whether is it stable or not stable, is there any factor that helps to stabilize it. Yeah, so the greater the Ka value, the stronger the acids. Okay, the lower the pKa, the stronger the acids as well. Yeah, so as what we mentioned earlier on, the strength and the concentration is not exactly related. They are different concepts. Okay, yeah, so over here we have questions, pH and degree of or degree of dissociation, reliable indicators of the strength. Okay, so I would say if you are, again, if based on what you understand about strong acids, so strong acid ionizes completely, so therefore extent of dissociation or degree of dissociation would be a more reliable indicator. Okay, so if again, I will open this up for discussion in the tutorial, so you don't really need to we don't really need to find out an answer over here. Okay, so moving on with exercise 2.8, you have questions here. In exercise 2.4, the pH and the degree of dissociation of a solution of ethanoic acid of concentration 0.1 were found to be. So earlier on, 2.4, let's see, what is the pH? 2.87. Okay, so the pH is given to be 2.87. Okay, so we'll write it down over here. So this would be 2.87. Degree of dissociation was found to be let's see, 1.34%. Okay, or you can put it as 0.0134 or 1.34%. Okay, so this is 1.34%. Okay, then you are supposed to number one, find the pH, okay, and B, the degree of dissociation of ethanoic acid of a lower concentration, which is 0.001 moles per dm cube. How have the pH and degree of dissociation affected by dilution? Okay, so this is a dilution of about 100 times. Okay, so if we try to work it out over here, so maybe I'll leave a bit of space. So again, ethanoic acid, so HA equilibrate to give us H plus plus. Okay, maybe I should put the actual one, so that I mean the more correct form, not the actual, the more correct form from what you have learned, for what you have learned in H2, so that there's some consistency. So we have an I stable over here. Okay, so again, the Ka value. So what is the Ka value of ethanoic acids? 1.8 times 10 to the power minus 5. Okay, so we'll write that in. So the Ka is equals to 1.8 times 10 to the power minus 5. Then 1, 2, 3. So we have 0.001, then dash dash dash, and then minus y, 0.001 minus y, and then this is plus y, and then y. Okay, then we have a K expression over here. So Ka is equals to y squared over 0.001 minus y. Yeah, again, we'll make the assumption that the extent of ionization is much lesser than 0.001. So from here, 1.8 times 10 to the power minus 5 will be multiplied by 0.001. Okay, and then this will be equals to y squared. Okay, and then we'll take the calculator and punch the value. 1.8 times 10 to the power minus 5 multiplied by 10 to the power minus 3, and then we take the square root. Okay, so we'll get y to be 1.342 times 10 to the power of 1, 2, 3, 4. 10 to the power minus 4 moles per dm cube. And then from here we can calculate the pH. Okay, so we'll try to determine the pH minus log base 10 of this. We'll get 3.87. Okay, so this 3.87 to be for the pH. Then what we're going to do now is we're going to determine alpha. Okay, so alpha, of course, alpha is simply y, which is 1.342 times 10 to the power of minus 4 divided by the initial amounts, which is 0.001. 0.001, and then multiply by 100%. I think there's no more space, so you get what I mean. So therefore, I'm just going to punch the calculator and determine the value. Minus 4 divided by 0.001 times 100%. So I'm going to get 13.4%. Wow, 13.4%. Okay, so you realize that as I perform 100 times dilution. Okay, so why is it 100 times? If you look at the initial concentration, it's given to be 0.1 over here. Okay, so I'm doing 100 times dilution, and then you notice that the pH goes from 2.87 to 3.87, so it increases. But the extent of ionization actually increases by 10 times, so we get 13.4%. Okay, so the more dilute the solution is, you expect the extent of ionization to be greater. Okay, so in this case, which is a better indication of strength of the acids? Okay, because the pH and degree of ionization actually change with concentration. Okay, I don't know whether you noticed that. Earlier on, we have a question. Of course, I mentioned that it's open for discussion, but of course, from this part, it seems to give us an indication of which is a more reliable indicator. Yeah, of course, whenever we want to compare across the different acids, I think what is fairer would be we need to ensure that their concentration are the same before we can discuss, because if the concentration is different, then I think the discussion will not make a lot of sense. Okay, so that's something which you might want to be aware of. Okay, so therefore you could use pH, you could use extent of dissociation to help you decide on which is a stronger or weaker acid, but that's provided that the initial concentration for all the acids which you want to compare with, or all the weak base which you want to compare with, are similar. Okay, maybe I wouldn't say the same, but similar. Okay, then the diagram over here will show you how the pH, alpha, and Ka change. Of course, Ka doesn't change, as you know, because Ka is a temperature dependent variable. pH will approach 7, okay, because as the acid become more and more diluted, the amount of H plus contribution become lesser and lesser, so it will approach the auto ionization of water, and then the extent of ionization will also increase, approaches 1. So for a very weak acid, you can tell that its extent of ionization is close to maybe 100%. Yeah, so therefore maybe we did mention a little bit about this, but Ka would be the best indicator of the strength, because Ka tell us the extent where the position of equilibrium is lie towards. Okay, then we have exercise 2.9 to end of section 2. Okay, so each of the following reactions contain 2 Bronsted acids and 2 Bronsted bases. Suggest with brief reasoning which is a stronger acid. Okay, so from here you get a Kc value that is very, very low. So that means that the position of equilibrium lies to the left. So if the position of equilibrium lies to the left, that means that OH minus is a stronger base as compared to ammonia. And that also means that the conjugate acid, in this case ammonium, is a stronger acid as compared to water. Okay, so from the position of equilibrium, whether it lies to the left or right, you can tell whether between the two pairs, between the pair from the reactant and the products, you can tell which is a stronger base and which is a stronger acid. Okay, and then of course for B, we have this particular species. You probably will not be familiar with it as of now, but I can draw it out for you. So it's actually phenoxide. So a phenol ring with an O minus, reacting with ethanoic acids. Okay, and in the course of reaction, I get phenol. So phenol looks like this, and then ethanoate. You notice that the value of Kc is in the magnitude of 10 to the power minus 5. So that means that POE, position of equilibrium, lies to the right. So if the position of equilibrium lies to the right, that is actually trying to tell you that phenoxide is a stronger base as compared to ethanoics. And ethanoic acid is a stronger acid as compared to phenol. Then some of you might argue, how come it can't be the other way around? Just imagine, if it's the other way around, then I'm not going to get a very high Kc value. I'm going to get a Kc value that is much lesser than 1. Okay, so just think about it and then see whether it makes sense. Okay, so therefore, in short, there is a principle which you might want to be aware of in chemistry. So when you are dealing with reactions involving Bronsted acid and bases, right? Yeah, the forward reaction will tend towards the formation of a weaker conjugate base and a weaker conjugate acid. Yeah, there will never be a reaction where you start off with a weak base and weak acid and you end up with a strong acid and strong base. Yeah, because if that is the case, the thermodynamics will actually drive towards the backward reaction. Yeah, okay, so if you're still confused, think about it. I think exercise 2.9 is a very good exercise for you to think about some of these cases. Yeah, okay, yeah, so with that, we'll end off section 2. Okay, we are going to look at section 3 on salt hydrolysis next. Okay, so what exactly is a salt? So similar to what you learned in secondary school, if there's a reaction between an acid and a base, you will produce a salt. Okay, so in this case, potassium hydroxide and hydrochloric acid reacts to give you potassium chlorate. Yeah, and you might be aware that the reaction between potassium hydroxide and hydrochloric acid essentially is an acid-base neutralization between OH minus and H plus. Okay, so therefore K plus and Cl minus, they are just what we call spectator ions swimming around the solutions. They do not take part in the reaction. Okay, and you probably learn a little bit that if a reaction involves a strong base and a strong acid, the end point of the reaction, the pH is actually neutral. Okay, so that actually tells you that K plus and chloride, they themselves, they do not undergo reaction with water. So they merely form ion dipole interaction with water molecules. Yeah, and then on the other hand, if the cations or the anions react directly with water, that is when salt hydrolysis takes place. Yeah, so this is the purpose of this particular section on salt hydrolysis. Yeah, so we want to reinforce, or we want to emphasize that many salts are actually a result of the production of either strong base, weak acids, or strong acid, weak base. Yeah, so because of that, the relevant salts, either the conjugate acid or the conjugate base, they themselves are weak base or acid themselves, so they are able to undergo a reaction with water to produce OH minus and H3O plus. Yeah, and later on you'll realize that some cations will also undergo hydrolysis because the cations have very high charge density. Yeah, so the cations themselves, they will be able to polarize the OH bond of H2O to a very great extent, and in the process produces a surplus amount of H plus. Yeah, so that aspect will be quite important in your inorganic qualitative analysis, and of course transition metal chemistry, which will come up later on. Okay, so in general, ions where the salts are derived from strong acid and bases, they do not undergo hydrolysis. So the final solution will be neutral at 25 degrees Celsius. Yeah, then the salts of weak acids and bases, as well as some of the cations with high charge density, as I mentioned earlier on, they will undergo substantial hydrolysis to produce solutions with pH greater than or less than 7. Okay, so for the next sections, I think we often talk about ethanoic acids. So again, we are just going to talk about ethanoic acid salts now. So sodium ethanoate is the salt formed from the weak acid, ethanoic acid, and the strong base, sodium hydroxide. Yeah, and ethanoic acid being a weak acid, so its corresponding conjugate base itself will be a weak base. But as a weak base, it is a stronger base than water. So in that case, it will undergo partial hydrolysis based on this particular equation. And in the course of this partial hydrolysis, it's able to produce a small amount of excess OH minus. And this small amount of excess OH minus will result in the alkalinity of the solution. Okay, so therefore, even when, let's say you perform an acid-base titration with sodium hydroxide and ethanoic acid, although ethanoic acid may be completely neutralized, the final solution is still alkaline. Yeah, so the alkaline nature of the solution is due to the fact that ethanoate undergoes partial hydrolysis in water, given by this equation, producing a surplus amount of OH minus. Okay, sodium plus itself does not undergo hydrolysis because of its low charge density. Yeah, so for sodium ethanoate, I think it's quite clear cut. The solution, I mean, if you buy sodium ethanoate itself, the salts, and you dissolve it in water, the solution will be alkaline. Okay, so for a strong acid and weak base, it's also the same thing. So that applies to many ammonium salts, because ammonium salts are produced from ammonia and a strong acid. Yeah, so ammonium salts are acidic in nature because ammonium cation is a stronger acid than water. Although it's a weak acid, but it is a stronger acid than water. So strong and weak are relative. So that is certain these are concepts which you need to come to terms with when you are dealing with acid-base equilibrium. Okay, so when I pass you, or when you dissolve ammonium chloride in water, you are going to get an acidic solution. Okay, so that is because the ammonium cation will undergo partial hydrolysis with water, and in the process you generate a surplus amount of H3O+. Okay, however, if I have a salt derived from a weak acid and a weak base, such as ammonium ethanoate, yeah, because ethanoate ionizes or hydrolyzes, ammonium also ionizes or hydrolyzes, you don't know what is the outcome of the final pH. Yeah, so the final pH of the solution depends on how strong the acid is as compared to that of the base. So if ammonium, let's say if the, okay, so in this case, I think we have all the three cases here. If the K of the cation, in this case ammonium, is bigger than the Kb of the anion, then the overall solution will be acidic, because now the cation is able to ionize to a greater extent, or slightly greater extent. If it's the same, then it's neutral, and then the other way around, if the anion is a stronger base, then solution will be basic. Okay, next we are going to move on to salts containing aqueous metal cation with high charge density. So this is an important portion for transition metal chemistry as well as your qualitative analysis. So you probably want to be aware that some of the cations with high charge density, such as Al3+, and off the top of my head will be chromium 3+, okay, and iron 3+, yeah. So these cations, they will partially ionize or partially hydrolyze in water, and in the process, they will generate H3O+. Yeah, so if you are interested, you can go to your data booklets. You can just roughly look at the data. Of course, the data booklet doesn't tell you which cation will hydrolyze, but you can use that to kind of like make a prediction. Remember, it's high charge density, so it's not just the cationic radius. So if you remember what I said, it will be Al3 plus. So the radius, the cationic radius is about 0.050. And then we're going to move on to the transition metal. Remember I said iron 3 plus. Yeah, so that's also about 0.055. And I think I mentioned, what is the other one? Chromium 3 plus. Yeah. So these are usually cations with +3 charged. And they have a cationic radius that is probably around 0.06 or less. Okay, so you notice that, for example, iron 3 plus with a radius of 0.055 nanometers, when you dissolve it in water, the solution is actually acidic. But iron 2 plus, the solution is not very acidic. In fact, it's very close to neutrality pH. Yeah, so the charge density, again, if you recall from what you learned in chemical bonding, is dependent on the charge over the cationic radius. Okay, and then we go back to this. Over here, basically, they are just trying to explain to you why it undergoes hydrolysis. Okay, so this is something you probably haven't learned in H2 unless you have read ahead and look at transition metal. So if we have a Al3 plus, most of the cations, except for group 1 cations, they tend to be surrounded by water molecules. So it's not always 6 water molecules, but at least for H2, most of the cases you met will be 6 water molecules. Okay, and because of the high charge density of the Al3 plus center, right, it will polarize the OH bond of every single H2O molecules. Yeah, so over here we just show you one H2O, but truth to be told, all the H2O, OH will be polarized. And because of that, the H tends to be loose quite easily to a H2O. Yeah, so because of that, then usually for quite a number of Al3 plus with 6 water molecules as the ligand, we call this the ligand, right? They will tend to lose the H plus to H2O to produce a surplus amount of H3O plus, even when you simply just dissolve it in water. Yeah, and that is why the salts of these cations tends to be acidic in nature because of the excess amount of H3O plus. Okay, so this is basically just schematics lah. I mean, to show you what exactly is happening, because most of you have learned organic chemistry. So when you look at this particular diagram, you can probably appreciate that the lone pairs on oxygen over here will undergo an acid-base neutralization and grab on the H, and then this particular OH group will become an OH minus. Yeah, so as the reaction proceeds, the charge reduces from +3 to +2. Okay, yeah. You will encounter more of this in the qualitative analysis part of your practicals. Yeah, so not to worry too much. Okay, and then yeah, so these are the cations which I mentioned earlier on as well, like chromium 3 plus and iron 3 plus. These are probably the few which they are a lot more relevant for H2. Okay, so I think it will be good for you to know these three. There are a lot others, but you don't usually encounter them. Even if you are required to use them, then there will be information given to you. Okay, so with that, let us look at exercise 3.1. You are asked to state whether the following solutions are acidic, alkaline, or neutral. Okay, so acidic, alkaline, or neutral. And then supposed to write equations, including state symbols for any hydrolysis reaction. Okay, so for A, you have potassium bromides. Okay, so for potassium bromides, I think you can guess that it is the salt of potassium hydroxides and hydrobromic acid. Yeah, so therefore it's the salt of a strong acid and strong base. I expect it to be neutral, so there won't be any hydrolysis. Okay, and then sodium carbonates. So for sodium carbonates, of course, sodium itself, it will not undergo substantial hydrolysis as what we mentioned earlier on, because it's a group 1 cation. Yeah, but carbonates, you might want to be aware that carbonate is actually the conjugate base of a weak acid. Yeah, what we call a bicarbonate, HCO3 minus. Yeah, and bicarbonate is the conjugate base of another weak acid known as carbonic acid, which essentially is not very stable in water. Yeah, so this will tend to be, it tend to form CO2 and diffuse away. Yeah, so that is why in secondary school, if you remember, carbonates usually react with acid to give you CO2, and that is the reason why. Because carbonate is a base, so you react with H plus to produce carbonic acid, so react with 2H plus to produce carbonic acid, and along the way, the equilibrium will shift towards the production of CO2 and H2O. So that is why you observe effervescence. Okay, so therefore carbonate is actually a weak base. So since it's a weak base, we will need to write an equation for hydrolysis reaction that is taking place. Yeah, so I'm just going to use a purple ink. So we will have carbonates reacting with H2O, and then equilibrates, so it hydrolyzes to give you OH minus and HCO3 minus. Now remember, when you are writing hydrolysis reaction, right, you are just supposed to increase in this case, since you are writing for a base, so you are supposed to increase the H of the base by 1. Do not go all the way to H2CO3. Okay, so remember this. Yeah, because there's no logic if it goes all the way. I think you have to think about it. Why is that the case? Yeah, so unless I spam or I add a lot of H plus in, if not, you will not go all the way to CO2. Okay, then for C, I think it's probably an example which you are a little bit familiar with. Chloride, as you know, is the conjugate base of hydrochloric acid, so therefore it will not undergo hydrolysis. But this particular cation is actually the conjugate acid of methylamine. Yeah, so it's similar to ammonia. So ammonia is a base, it's a weak base, so methylamine is also a weak base. Yeah, so again, you expect methyl ammonium, so this particular conjugate acid, to undergo partial hydrolysis in water, and in the course of the reaction, it gives you a little bit of H3O plus and the conjugate base, in this case methylamine. Okay, then for D, we have ammonium hydrosulfide or hydrogen sulfide. Yeah, so NaH4 plus, so we have NH4 plus, and then we have HS minus. We are given the Kb of ammonia and Ka1 of H2S. Okay, then you'll be wondering how useful are these data, and then what are they? Why are we given the Kb of ammonia and the Ka1 of H2S? You are given that because from here, right, you can derive the Ka of ammonium. Okay, how do I derive the Ka of ammonium? So essentially the Ka is simply the Kw, which is 10 to the power minus 14, divided by the Kb, which is 1.8 times 10 to the power minus 5. Okay, so if we take a calculator and punch, we should be able to get an answer out. Okay, let me try that. Just a moment. Okay, yeah, so you should be able to get 5.6 times 10 to the power of minus 10, or 5.56. Maybe we leave it as 3SF, 5.56 times 10 to the power minus 10 moles per dm cube. Okay, then we can do the same. We are given Ka1 of H2S. So in case you are not very familiar, so H2S is what we call a dibasic acid. So it will ionize twice. So the first ionization, I will be able to get H plus plus HS minus. The second ionization, I will be able to get H plus plus S2 minus. So this is Ka2. Yeah. So in order to find out the Kb of HS minus, I will need to find the correspondence Ka1, which is associated with H2S. Okay, so in this case, I'm going to use the value of Ka1 to find the Kb of HS minus. Okay, so with that, then I'm going to find Kb, which essentially is 10 to the power minus 14, divide by 9 times 10 to the power minus 8. Okay, so just a quick calculation for me to get the answer. Okay, so I'm getting 1.11 times 10 to the power of minus 7 moles per dm cube. Okay, but what is most important is please take a look at these magnitudes. The magnitude of the Ka of ammonium is in the region of 10 to the power minus 10, but the Kb of HS minus is in the region of 10 to the power minus 7. Yeah, so therefore HS minus is a stronger base than ammonium as an acid. And because of that, I expect the hydrolysis of HS minus to be slightly more substantial as compared to the hydrolysis of ammonium. So I expect the overall solution to be alkaline because there should be a slight excess of OH minus as compared to H plus. Okay, yeah, so because of that, solution will be alkaline. Yeah, in case I didn't mention earlier on, this is neutral, this will be basic or alkaline, this will be acidic, and then this will be alkaline. And then iron 3 chloride, I think we briefly talked about that just now because chloride is the conjugate base of hydrochloric acid, so chloride will not undergo hydrolysis. But iron 3 plus is the cation with a high charge density given here, so it will undergo relatively substantial hydrolysis to give me an acidic solution. Okay, so because of that, I'm going to write a balance equation out. So I'm going to expect this is known as hexa aqua iron 3 complex. Okay, hexa aqua iron 3 complex with a H2O molecule. Then you will undergo hydrolysis to give me Fe. Then H2O will reduce by 1. Okay, overall charge will reduce by 1 as well. And then I will have H3O plus. Okay, yep, I forgot to write for D, so maybe you can write on your own. So the main reaction is probably HS minus plus H2O. H2O will be a liquid, and I'm going to get H2S plus OH minus. So technically you should be writing for ammonium as well, but this is probably more substantial. Yeah, so there should be a slight excess of OH minus. And then for 3.2, for 3.2, okay, so before that, we need to look at the pH of salt solutions. Okay, so again, we need to consider the strength of the acid and base, and then write an equation and then see which one produces a surplus amount of H3O plus and OH minus, and then after that calculate the concentration of H3O plus or OH minus. So I think it works best with an example. Yeah, so in this case, we have sodium ethanoates. So again, sodium plus does not undergo substantial hydrolysis, so we will ignore sodium plus. Okay, so we have ethanoates. So CH3 CO2 minus equals plus H2O equilibrate to give me ethanoic acids plus OH minus. Okay, and then I stable. Okay, given the concentration to be 0.10, and then dash dash dash, and then minus X plus X plus X. So 0.10 minus X, X. I am defining Kb over here. I'm not given Kb, I'm given Ka. So in this case, from Ka, I need to find Kb. So that will be 10 to the power minus 14 divide by 1.8 times 10 to the power minus 5. Okay, and this will give me 5.0 0.56 times 10 to the power of minus 10 moles per dm cube. Okay, so since I have already written out a Kb expression, that will be x squared over 0.10 minus x. We assume x to be much smaller than 0.10. Remember, this is an assumption. Assume. Okay, so therefore Kb will be 5.56 times 10 to the power minus 10 multiplied by 0.10 equals to x. So there will be square roots. So x will be equals to 7.45 times 10 to the power minus 6 moles per dm cube. Okay, so from here we can calculate POH minus log base 10, 7.45 times 10 to the power minus 6. I will be able to get 5.13. So pH will then be equals to 14 minus 5.13. I will be able to get 8.87. Yeah, so the overall pH is above 7. Okay, so we are going to do the same thing for ammonium chloride. Okay, so ammonium chloride is the conjugate chloride is a conjugate base of a strong acid, so it will not undergo substantial hydrolysis. So ammonium will be the one which will undergo hydrolysis. So I'm going to get ammonia equals plus H3O plus aqueous. Okay, so again, I stable. Ammonium concentration is given to be 0.450 dash dash dash. Okay, so we let it be y, so minus y plus y plus y. And then equilibrium concentration of ammonia will be 0.450 minus y, and then y. Okay, Kb of ammonia is given to be 1.78 times 10 to the power minus 5. But for this particular equation, we are defining Ka because we are looking at the hydrolysis of the conjugate acids. Okay, so we need to find Ka, so therefore Ka is equals to 10 to the power minus 14 divided by 1.78 times 10 to the power minus 5, and from here we are going to get a value. Let me just calculate to see what I'm going to get. 10 to the power minus 14 divided by 1.78 times 10 to the power of minus 5. Okay, so I'm going to get 5.62 times 10 to the power minus 10 moles per dm cube. Okay, and from here I'm going to substitute this in, write a K expression. So Ka will then be equals to y squared over 0.450 minus y, and because we assume that y is much lesser than 0.450. Therefore, I'm going to get 5.62 times 10 to the power of minus 10 equals to y squared over 0.450. Okay, and then I shift the things around, so y is equals to square root of 5.62 times 10 to the power of minus 10 times 0.450. Okay, so from here I'm going to get 1.59 times 10 to the power of minus 5 moles per dm cube. Okay, I'm going to calculate pH, which is minus log base 10 of 1.59 times 10 to the power of minus 5, and I will be able to get 4.80, which makes sense because this is the conjugate acid of a weak base, so it will undergo substantial hydrolysis or some form of hydrolysis in water, and I'm going to end up with an acidic solution. Okay, so with that, we are done with section 3, and do watch out for the next video for section 4 onwards, which is on buffer solutions.